So in this lecture, we're going to talk about change of coordinates, specifically for integrals of 2 and 3 dimensions. Let's recall that in first semester or second semester calculus, one of our first techniques we have for evaluating integrals is by substitution. So let's say in Calc 2, we learn the technique of integration by substitution. So for instance, a super simple case would be if I wanted to integrate, say, e to the 2x, say from 0 to 1 of dx, I might take du to be 2, and then du is 2 dx, and then my limits change from x limits to u limits from 0 to 1 to 0 to 2, and then I don't have a 2 here, so I put a 1/2 out front. I get e to the 2x 2 dx, which becomes 1/2 e to the u from 0 to 2 du. So I just get 1/2 e to the 2 minus 1. So we learned that technique, and this is integration by substitution. One important thing to keep in mind here for this is what we're really looking at is we're trying to change the function here. The region we're integrating over is just an interval. So when we do the substitution, that just changes to an interval too, and we don't much care about that. We have to adjust it, but we don't pay much attention to it. So for this case, so in Calc 2, we focus on changing the function. Now for our integrals, for this lecture, we're going to focus a lot more on changing the region than changing the function. Obviously, we will have to change the function, but the region takes the precedence here. So that's going to be more what we're focused on. So let's look at an example of the type we've already looked at before, but we want to rephrase this a bit. So let's consider the following integral. So we go from 0 to 1, 0 to square root of 1 minus x squared. And let's not care about the function so much right now. And look at this dy dx. So now, if I think of this region as R, we can graph this region as follows. So this is just this region here, where the circle here is x squared plus y squared equals 1. And then we want this region here. And let's call this region, say, R. Now, what we've seen before is this isn't a great way, rectangular coordinates aren't a great way to do this integral. So we made the change to polar coordinates. So this is one of our first examples of actually changing coordinates in 2 space here. So when we did that change, if we're integrating over this region R, then this becomes a nice simple region where the radius goes from 0 to 1, and my angle goes from 0 to pi over 2. And then of course we have to change the function, and then our dA became R dr d theta. So let's revisit this a bit and think about what's going on here in terms of our 2 coordinate planes. So I can graph my region in the r theta plane here, and this is the whole reason we switch to this plane is we get a nice region in this case. So my r just goes from 0 to 1, my theta goes from 0 to pi over 2, and I have a region that looks like this. Whereas in the xy plane, we saw above, our region is not so nice because it's part of a circle, so it looked like this. So we can think of what we're doing is we're transforming this region on the right to the region on the left when we do this change of coordinates. So we're kind of going to transform like that. So let's think about what the dA was in each region and see kind of what's happening. Before we do anything more formally, we can kind of just informally see what's happening. So if I'm looking at my region on the left here, when I look at a little piece of this region here, this is delta r delta theta, and say this is going from, say, 1/4 to 1/2 in this region, and let's say maybe pi over 8, this is going to pi over 2, this is going to 1, and say pi over 4 here. When I for that and see what that looked like, the corresponding region looked like in the xy plane, well, I could start with drawing these two angles. So we go out like this. So this is the angle pi over 8. This is the angle pi over 4. And then I want to have my radii here as well. So this is 1/4 and 1/2. So my region here becomes this region in between these. And that's what my region looks like in this plane. And so that's where we see how we had this before. This is the delta r, and that region there is the r delta theta. So we can think of the reason we have that r when we're doing when we're changing the polar coordinates is because this rectangle over here in the polar region stretches out in the xy coordinates. So that's how our transformation there looked to get our region. So the delta r, delta theta over here, the region over here became having area in the xy plane as r, delta theta. So there's some kind of stretching going on there is what's happening when we switch coordinates like that. So that's something we've seen before. Now we want to look at this more generally and see how our situation sets in more generally. So let's look at this. We want to look at a situation that will kind of encompass most of anything we're going to look at in 2 space, and then we'll see how to do it in 3 space as well. Okay, so let's suppose we have variables u and v. And let's suppose we can write x as a function, x and y as a function of these, with, say, x is equal to some function in terms of u and v, and y is some function in terms of u and v. And so what you want to think of here is what we just did. So if we took r and theta, then x of r theta is just r cosine theta, and y of r theta is r sine theta. So this is just making more general where we're using u and v and not fixing it to be r and theta, so we can use other variables as well. So now let's draw some pictures here of what we want to look at. So let's start in the UV plane, and let's draw a little rectangle in the UV plane here. So suppose we have some region we're going to call our region V in the XY or in the UV plane, but let's just look at a little piece of that region. So let's call this Vij. And let's say down here, suppose this is the value UV. So this one goes over a little in the U direction. So we get this, and then this one goes up a little in the V direction. So we get this. And now we can look at the corresponding region in the XY plane and see what this looks like. So let's maybe give this a different color. And so we're going to start down here at this point. And this point now is x of u plus, or just u. Sorry, this is x of uv, y of uv. And then maybe we're going to have this goes up somewhere here. And this point is x of u v plus delta v, y of u v plus delta v. And then maybe we go up like this. So this is going to go, my region is going to kind of cover up there, but this one here is going to be x of u plus delta uv, y of u plus delta u. comma v. So those are our points there. Now we do have to make one assumption here. So we're going to call this R of ij for our region in the xy plane. So this is the region we're looking at here. Now this transfers here by taking x of uv, y of uv is our map that goes from one to the other. And we need this map to be what we call 1 to 1. So another way of saying that is each point in R of ij comes from exactly one point in V of ij. So you can think of you're taking the V of ij and you might be stretching it out in some different directions, but each point in Vij goes to only one point in R of ij, and each point of R of ij comes from exactly one point in V of ij. So just think of V of ij like being elastic, and you're going to stretch it in some different directions, but you're not going to fold it on top of itself or anything crazy like that. You're just going to stretch it out so it fits. So now what we'd like to do is we'd like to figure out what is the area of Rij. So if we think back of what we did in our other case, remember when we transferred from the polar here, so you can think of the transfer here as you're taking r and theta, and these are mapping to r cosine theta, r sine theta. And then we wanted to know, well, what did a little piece of area here, if I did that transformation where I took r theta to r cosine theta, r sine theta, how did that change the area? So we wanted to know what was the little delta area in the xy plane, and that's what we calculated as r delta theta. So we want to do the same thing here. So what is the area of Rij? Well, what we're going to do for this is we're going to look at some vectors here. So let's just draw this by itself now. Let me go back to my orange and say I have, this is my Rij. Well, now I'm going to create vectors here. So let's call this vector going along the bottom here A, and the vector going in this direction B. So if I do that, we can recall from our cross product is that the area of Rij is the magnitude of A cross B. So now we just want to figure out, well, how do we calculate that? Well, remember we know what these points are. So A is, well, the change in the x values. So x of u plus delta u, v minus x of uv I, plus y of u plus delta u v minus y of uv j. And that's just given by the fact that this point here was x of uv y of uv, and this point here was x of u plus delta uv y of u plus delta uv. And then just using how we find a vector between 2 points. And so if we think about what this looks like, this looks almost like a partial derivative. So this is approximately delta x delta u, but then I need to put that delta u in the bottom. So maybe let's write this out a little bit more carefully here. So this is, if we want to rewrite this, I can write this as x of u plus delta uv minus x of uv over delta u, and then multiply that by delta ui. And similarly, so just inserting in a delta u in the top and bottom, so we're really not changing anything. And then we can say this is approximately delta x, delta u, delta ui, plus delta y, delta u, delta uj. And so that gives us a good approximation for the A. And of course, the smaller the delta u is, the better this approximation is. So we can do the exact same thing for b, and if you go through that process, which it would be a good idea to do that, we get this vector. So those are the vectors spanning my parallelogram Rij there. So now we can go ahead and calculate that area. So first let's calculate this cross product. So this is ijk, and then I have delta x, delta u, delta u, delta y, delta u, 0, delta y, or delta x, delta v, and delta y, delta v, and 0. And if we write out what this is and do the cross product here, this is just delta x, delta u, delta y, delta v, delta u, delta v, minus delta y, delta u, delta x, delta v, delta u, delta v, k hat. So the area of Rij is the magnitude of this. So this is going to be magnitude of delta x, delta u, delta y, delta v, minus delta y, delta u, delta x, delta v, delta u, delta v. And so that gives me the area of Rij. So this part here, this is pretty important. So one thing to note is I can write this as the determinant of a matrix. And we do this because this shows up often and because it's going to be important for the more general cases. So you can just check delta. We do this determinant. It's delta x, delta u times delta y, delta v minus delta x, delta v minus delta y, delta u. And this thing here, this is given a special name. This is called the Jacobian. And we write so delta xy over delta uv. And so we're going to actually set this to be the absolute value, or yeah, just the determinant is fine. Okay, so that's just this determinant, delta x, delta u, delta x, delta v, delta y, delta u, delta y, delta v. And of course, if you want to write this with a little bit shorter hand here, we can use the shorter hand notation here. So that gives me how the area of the Rij's. So now if we add all of these up for all of the rectangles in the region R, where R is our region in the xy plane, well, this is the sum over all ij's. Well, it's approximately the sum. To take limits to get the actual sum. So let's use, we have to pick some points in each little rectangle. So that would give me this integral approximately. And so then this is approximately the sum over I and j, f of xij, yij. Remember, xij, yij is just some point in the little rectangle. And then we get the absolute value of the Jacobian delta u, delta v. Now, each point in Rij, we know comes from one in Vij. So each xij, yij can be written as some point coming from the other region. So I can write this as x, uij, vij, or y, uij vij for some uij vij in that little region vij, capital Vij. Right, so if we look back, let's go back up here and think for a second. So if I pick some point here, xij, yij, there's some point over here, uij, vij, that maps directly to that point. And there's only one point that does it. So if we do that, then we can change the integral again. So going back to what we had, well, this is then approximately the sum over I and j, and then let's rewrite this with x of uij vij, y of uij vij, then the Jacobian delta u delta v. But now notice everything here is in terms of u's and v's. So certainly the inputs to the f's is in terms of u's and v's, delta u and delta v, and then remember our Jacobian here is given in terms of u's and v's. So this is a Riemann sum. In u and v. So then if I take the limit of this integral that we started off in the xy plane, and let's take the limit as delta u goes to 0 and delta v goes to 0 of this sum, which I'm going to write all out again. Well, this is exactly the integral over the region v, so the one in the xy plane, or in the uv plane, of the function f of x uv y of uv, and then this Jacobian du dv. So that shows us how we change variables there. This thing here, basically, the Jacobian, is what's scaling the area to change from the regular rectangle in the uv plane to whatever the shape is in the xy plane. So that was quite complicated. So that was very complicated. So what we want to do now is let's go back and look at our example from before and kind of see where everything fits together in this new framework that we just did. So let's look at this region again, where we were looking in the xy plane, where we just had this circle here. And this circle was of radius 1, and this is my region R. So now in this case, let's think about what our Jacobian looks like. So I know x is r cosine theta, y is r sine theta. So then if I put this in terms of my Jacobian, this becomes, let's take the absolute values off for a minute. Just do just the Jacobian. So this is going to be x with respect to r, x with respect to theta, y with respect to r, y with respect to theta. And so this is just cosine theta, and then minus r sine theta, and then this is sine theta, and this is r cosine theta. So when we take this determinant, I get r cosine squared theta minus minus, so plus r sine squared theta, which is r cosine squared theta plus sine squared theta, which is just r. So when we make that transformation, what we're getting is that integral over r of f of xy dA is the integral over the region V, which is f of r cosine theta, r sine theta, and then we get that Jacobian, which is r, and then dr d theta. So this is the Jacobian. So that shows you where that r is actually coming from. It's that Jacobian. And what did our region V look like? Well, we saw that before. That region V was just this region that went from 1 to pi over 2. So we can finish writing our integral out now. 0 to 1, 0 to pi over 2, f of r cosine theta, r sine theta, r dr d theta. So now we see from that more general setup exactly where we're getting that r from. So let's see another example we can do with this to recover a result we might or might not remember from geometry. So let's consider the ellipse. X squared over a squared plus y squared over b squared equals 1. And let's see, so let's show the area is pi AB. So like I said, this might be something we know, it might not be something we know. Let's go ahead and graph this. So this is, we're going to think of this as our region R in the XY plane. So let's just think of it something like this. Now I want to make a transformation here that gives me R but has a nice region to start with. So what could we do? Well, let's take X, or let's take U, X to be A times U, and Y to be B times V. And if I do that, then what gets mapped to my region here if I'm going to my UV plane? Well, the equation in the UV plane, well, I know X is A over U, so this would be A over U squared over A squared plus B over V squared over B squared equals 1. So that's equivalent to U squared plus B squared equals 1. So in the UV plane, the region that's actually mapping to what we're interested in is just a circle of radius 1. So this is U squared plus B squared equals 1. And so now we have a nice region here. Let's calculate our Jacobian. So the Jacobian, which is XU, XV, YU, YV, is just A, 0, 0, B, which is A times B. So then if I want the integral over my region R of 1 dA, which is this is the area of the ellipse, well, we know then that this is the integral over the region V, which we'll write here is V, of, well, our value change, well, there's no function to change there, and then I have my Jacobian AB, and then du dv, and so this is AB integral over V du dv. Well, this is AB times the area of V, which is just AB pi 1 squared, so pi AB. So we recovered the formula for the area of an ellipse just from looking at the change in coordinates. Now we can also use this change of coordinates to recover our spherical coordinates. It's just a little messier, but let's go ahead and do that. So we can also do this in 3 or more dimensions. So we're just going to focus on 3, but you'll be able to kind of guess how it would work in more. So in this case, let's say x is equal to x UVW, y is equal to y of UVW, and z is equal to z of UVW. So then our Jacobian in this case, which is delta of xyz over delta of UVW, this is going to be x with respect to u, x with respect to v, x with respect to w. Remember, this is the determinant here, so we've done 3 by 3 determinants when we did cross products, so we know how to do this. If you do more variables, you have a bigger determinant, which we necessarily haven't seen in multivariable calculus, but maybe if you've seen linear algebra, you would have seen it. So then if E, say, is the region, maybe we'll use curly letters here. So if E is the region in the XYZ space, so this is some 3-dimensional region, and let's say curly F is the region in the UVW space corresponding, so let's say mapping to E, and the change of variable formula is just given by, now we're integrating over E of f of xyz, and we're integrating a volume, so dv. So this is going to be then the integral over our curly f region of f of x UVW, y of UVW, z of UVW. Then we want the absolute value of our Jacobian. And then du, dv, dw. So just like before, we just have more variables in this case. So now the question is let's go ahead and work through what is the Jacobian for spherical coordinates. And this is messier because we're going to have a 3 by 3 determinant to do, but we're going to recover exactly what we saw when we did integrals in spherical coordinates. So let's recall our formulas here. And so our Jacobian so this is this determinant. Now we have to take these derivatives. So if I take the derivative of x with respect to rho, I get sine phi cosine theta. Then if I take it with respect to theta, I'm going to get minus rho sine phi sine theta. And if I take it with respect to phi, I get rho cosine phi cosine theta. And similarly, if you do the rest of these, you get sine phi sine theta, rho sine phi cosine theta, rho cosine phi sine theta, and then for this one you get cosine phi, and since there's no theta, that one's 0, and then minus rho sine phi. And now we have to evaluate this determinant, which is a mess, but so you take the first entry, so sine phi cosine theta, and then we take the smaller determinant left over, so we cover the first row and first column, what we get left. And then we do minus, and then the next one is going to have a negative rho, sine phi sine theta, and then the determinant that's left over is sine phi sine theta, rho cosine phi sine theta, cosine phi, and then minus rho sine phi. And then finally the last term is rho cosine phi, cosine theta, and then the determinant left over is sine phi, sine theta, rho sine phi, cosine theta, cosine phi, and 0. And now we have to take all those 2 by 2 determinants. So if we do that, I have sine phi, cosine theta, and that's multiplied by minus rho squared sine squared phi, cosine theta. And then I have plus rho sine phi, sine theta, and then inside I have minus rho sine squared phi, sine theta, minus rho cosine squared phi, sine theta, and then finally the last one, rho cosine phi, cosine theta, and then a minus rho sine phi, cosine theta. Now we've got a lot of simplification to do left, but most of this comes pretty quickly. So if I multiply this out, I get a minus rho squared, and then in the first term I'm going to get a sine phi, cosine squared theta, sine squared phi. And certainly you could bring those together, but we're going to choose not to bring the sine phi and the sine squared phi together. We get minus rho squared, and I'm going to get a rho squared. Let's leave the sine phi and the sine theta out front for a second. And then notice we can factor a rho out, and we can also factor another sine out. So I get a sine squared, and then what's left inside will be sine squared phi plus cosine squared phi. And then for the last one, I'm going to get a negative rho squared, and then I'm going to get a cosine squared phi, a sine phi, and a cosine squared theta. And now the sine squared and cosine squared become 1, so this becomes minus rho squared. Let's just bring the minus rho squared out front of everything. So I'm going to get a sine phi, a cosine squared theta, a sine squared phi, and then I have plus, and what's left over is sine phi, sine squared theta, and then I get a plus cosine squared phi, sine phi, cosine squared theta. And so notice if we take, say, this first term and the second term, I can factor out a cosine squared from both of those and a sine phi, and I'll get a sine squared phi and a cosine squared phi, and then I have left over sine phi, sine squared theta. So this sine squared phi plus cosine squared phi becomes 1, so I get minus rho squared, and I get sine phi, cosine squared theta plus sine phi, sine squared theta, and again factor out the sine phi, and then cosine squared plus sine squared is 1, so I get minus rho squared sine phi. So now if I look at my integral, now that I've calculated the Jacobian, even though it was a giant mess, it was doable. This becomes the integral over f of rho sine phi cosine theta, rho sine phi sine theta, rho cosine phi. And now I get absolute value of the Jacobian, d rho, d phi, d theta, and that gives us exactly the transformation formula for spherical coordinates, because that absolute value gets rid of our negative there with the rho squared sine phi. So even though we drew that nice picture when we were doing spherical coordinates to get where that rho squared sine phi was coming from, we see if we just do change of coordinates, it falls out automatically, which is quite nice. Now, that shows how we do things in 2 and 3 dimensions. We might ask, well, what about 1 dimension? Right, so the case we were most familiar with from Calc 2, well, there's a few caveats here. Remember, we needed our functions above to be 1 to 1, so we need our substitution to be 1 to 1. So if we're saying, so if we want the interval, if we consider the integral, say from a to b of f of x dx, and we want to make a substitution, say u is equal to g of x, we need g of x to be, we need g to be 1 to 1. So that means g inverse exists as a function for us. So if g inverse exists, then to put it in our framework above, remember we wrote x as a function of the other stuff, so we want to write x is equal to g inverse of u, and that's our transformation. And so our Jacobian in this case, it's just 1 by 1, so this should just be dx du. But now we've got to figure out, well, how do I take the derivative of this inverse function, which is something we saw when we were in Calc 1 when we were taking derivatives of inverse functions, but let's recall how that goes. So this is kind of an aside or a refresher from Calc 1. If I have this equation, if I take the derivative of both sides, well, on this side, this is certainly just 1. And on the left-hand side, we have to use chain rule. So I have f prime of f inverse of x times the derivative of f inverse of x. And all of that's equal to 1. Now I'm interested in the derivative of f inverse. That tells me the derivative of f inverse of x is 1 over f prime evaluated at f inverse of x. So that's just a little refresher from Calc 1 about the derivative of the inverse. So for us, remember we have x is equal to g inverse of u. So that means dx du should be d du of g inverse of u, which we just calculated. This is g prime of g inverse of u. So now with all of that in mind, with the Jacobian, if we were to rephrase this in terms of our new language, our new interval is GA to GB, then I have f of g inverse of u, and then the Jacobian, which is g prime over g inverse of u du. And now that looks a little weird compared to what we're used to doing for integration by substitution. So maybe let's do an example and see how this translates back. So let's consider integral from 0 to 2 of 2x e to the x squared dx. And now what I'd like to do is we want to set, I want my u to be x squared here. Well, notice this function, this is invertible on the interval from 0 to 2. So if I would have gone from -2 to 2, this wouldn't work because it wouldn't be invertible and we wouldn't be able to use this new framework, which is fine. We know how to do this substitution anyways. This is just kind of to show we can phrase it in this language, even though we would never want to do that. So for us then, x is equal to square root of u. This is gu inverse. So now, of course, our old method would just give 0 to 2, 2x, e to the x squared dx is the integral from 0 to 4 e of u du. So that's the old method. And we should recover the same thing with the new method. So let's see how that works. Well, let's think about what our derivative is. So we know that dx du, well, this is 1 over g prime of g inverse of u. So if we think of that g prime of u, remember g of u here is just given by the square here. So g of u would be u squared. So g prime of u would be 2u. And the inverse there, of course, is u inverse. So this would be g prime of u is 2u. So 1 over g prime of g u inverse would be 1 over 2 square root of u. So if I think about what's happening here, and you can also notice in this case, this is also just take the derivative. You can check that exactly because we know what the inverse is in this case. So we don't need the formula from before, but that shows that our formula does actually work. So now if I do the Jacobian, this is the integral from 0 to 4, and then I get my e of u because that's just doing my substitution. And then, of course, let me write it in order here. So 2, and then x, of course, is square root of u, and then eu, and then this should be my Jacobian, which is 1 over 2 square root of u du. And we see these cancel exactly like we would want them to, and we get e to the u du. So it might be a good idea to make sure you kind of understand what's going on here. Go ahead and work through another u substitution from Calc 1, calculate the Jacobian of your transformation, and see that it actually works out the same. You would never actually do a u substitution in Calc 1 using the Jacobian, but it does actually make sure you understand what's going on. And you can go ahead and try some two-dimensional and three-dimensional integrals as well. You could do some other transformations that don't just involve spherical and rectangular coordinates to see that those work as well. This material is super important for physics. So if you're going to study physics, you really have to understand this change of variables and change of coordinates in 2 and 3 dimensions and even higher.